Hi, my name's Abe, and today I'm going to go through an example of a related rates of change problem. Now, related rates of change problem's a little harder than just a normal rate of change problem because it involves more than one variable. So the best way to teach this, I think, is to run through an example. So here it is. We've got a tap filling a cone with water, and the question tells us the shape of the cone, what the angle is at the bottom, and also it tells us how quickly the water is going into the cone. And it goes, find the rate of change of water surface area over time at t equals 5. Okay, so I'm going to go through the steps with you. The very first thing you should do is figure things out. Want, have, need. Don't start thinking about iPads or anything. But what you see is that you want to go look at the question and you want to find what it is that you're after. Okay, very quickly. Go to the question. And you see that you're after the rate of change of water surface area over time. Right? So you want dA dt, where A is going to be the water surface area. Okay? Now, what do you have? Go to the question again and see what rate you've been provided. You've been provided with 8 centimeters cubed per second. So the volume of water going inside the cone per second. Or, in other words, dV dt, right? Change in volume over change in time. And what do you need? I'm going to put an equal sign here because generally it's a chain rule kind of relation. So what you need is basically you look at, well, okay, what will multiply with dV dt to give me dA dt? So obviously V is not going to be part of the final equation, so you want dV on the bottom and you want dA on top, because the idea is that when you put these together, the dV's will cancel and you'll get dA dt. Very simple, right? And that's it. That's the first step. Figure out what you want. So here, you see that what you're after is dA dV. Okay. Very simple. Very simple. So, let's move on to the second step. The second step is not very difficult either. In fact, the second step just says find what you need. Okay, it's not too hard, is it? Find what you need. So remember, what we need is dA dV, right? To find dA dV, perhaps you'd want a relationship between A and V. So what you're really after is A in terms of V. Remembering here that A is the surface area of the water, V is the amount of water in the cone. Okay. First of all, you want to write down what you know already. Alright? So you know that the surface area of this cone, right? Let's go back to that cone for a sec. This cone, the surface area is basically going to look kind of like this, right? And the area is determined by, sorry if you cannot see that, but that's a R in there, a radius, right? So the area of a circle is determined by the radius. I'm pretty sure you all know that. So you know, coming back to this page, that area is pi r squared. And you also know this. You also know that the volume of a cone is 1/3 pi r squared h. Don't need to remember that. That lives on your cheat sheet, I believe. So, okay, given what you know already, let's find a way to get to what you want. So you want A as a function of V. Currently, this is what you have. A as a function of R. Not exactly what you want. So perhaps you could get a relationship between V and R. If you can relate v and r, you can sub you can sub v instead of r, and so get a relationship between a and v, which is what you want, right? So you want to relate v and r then. So let's do this. You see that here v depends on r and h, right? So you need to eliminate one variable. Eliminate something. Going back to our cone, you see that it's open 60 degrees. Would you agree that the side section, cross section of our cone would look a bit like this? Now, if the bottom opening is 60 degrees, that means half of it is 30 degrees. The top thing here is r, and h is the height of the cone, which is here. H, right? Now, you see that you can relate r and h very easily using some trigonometry. So, coming back here, you will notice that tan 30 equals r on h, or h equals r on tan 30, which is equal to r on 1 on root 3, which is root 3 times r. H equals root 3r. So you just sub that back into the volume equation, and so you'll get v equals 1/3 pi r squared times root 3 times r. So put that all together, you'll get v equals pi r cubed over root 3. Pretty simple, right? Alright. So we're not done quite yet, because what you want is to sub r back into you want a relation between v and r, and then sub r out of this equation here. You want to sub r out and replace that with v. So let's get on to the next page, and we'll continue with this step. So this is still find what you need. Continued. Oh, sorry, thick pen. Not what I wanted. So remember from previous that we already have this. We have v equals pi r cubed over root 3. And remember that we have a equals pi r squared, and we want a as a function of v. Alright, write in my normal color now. So what can you do? Find out what r equals and sub it into a, right? So from here, you know that if you rearrange, you'll get r cubed equals root 3 times v over pi. So r equals root 3 times v over pi to the power of a third. Simple. Okay? Now you put that into a. A is pi r squared, right? Where r is what we found just below. So put that in. The power of 1/3 squared is the power of 2/3, like that. Okay, now that's sort of what we have, but let's make things a little nicer. Collecting like terms, the power on pi is, so here's pi to the power of 1, right? So you've got pi to the power of 1, and then divided by pi to the power of 2/3, you get pi to the power of 1/3. You've got root 3, which is 3 to the power of half, inside a power of 2/3. So half times 2/3 gives you 1/3. So you have 3 to the power of 1/3, and then v to the power of 2/3. Okay, cool. That's what a is. We found a in terms of v, but remember, what we really want is dA dV. So the simple way of doing this is saying, okay, let's just differentiate A with respect to V. And you'll notice that this first part here is a constant. Don't need to touch it. So I'm just going to put down this thing. 2/3 pi to the third, 3 to a third, V to the power of negative 1/3. Right? Simple differentiation. Okay. So now, just to tidy things up nicely, I'm just going to put all these bits inside a bracket again and put all that to the power of a third. And there you have it. dA dV is 2/3 3 pi on V over a third. That's what we've found what we want. Simple. Okay. The next little bit. New page. The next little bit says part 3 put back into original equation and check question. So basically, you want to know that what you're answering is the correct question. Okay, pretty simple. So, reminding ourselves again of what we saw at the start, we had dA dt is equal to dV dt times dA dV. Right? Simple. Now we know that dA dV equals 2/3 3 pi on V to the power of 1/3. Right? From the previous slide. We also know that dV dt equals 8. Just from the first slide. 8 centimeters cubed per second. So all you need to do is sub these in. 8 times 2/3 3 pi on V to the power of a third. Are you quite done yet? Yeah, you found dA dt, right? But actually not quite, because if you look at the very first part of this question, so just going back, here we go, you'll see that you want, what do you want? Rate of change of water surface over time at t equals 5. T equals 5. That's what you're after. So how can you get there? Well, you've got dA dt, but the problem here is that you have this variable v. You don't want v, you want t, right? How do you change v into t? Well, very simple. We have a relationship here between v and t, right? If dv dt equals 8, v equals 8t. Because v equals 0 at t equals 0. That's what you assume in the question, because we don't say that there was already water in the cone. So, simply sub v for 8t, and you'll get this. 3 pi on 8t over a third. There's ways to simplify this, of course, but that's not what we're interested in. We want to find what happens at t equals 5. And so at t equals 5, dA dt equals 16 on 3, 3 pi on 40 to the power of a third. And yeah, that's going to be your final answer. If you were to use a calculator, you would find that this is roughly 3.3. 3.3 what? Remember that we are dealing with units whenever we talk about rates of change. Going back to the first slide, we see that the unit that we've been given for time is seconds, and for like things like distance, area, volume is centimeters, or centimeters squared, centimeters cubed. Okay, so coming back here, we're looking after an area, so it's 3.3 centimeters squared per second. Notice that this part up here could be simplified further if you really want. You could actually put that down to 8 on 3 pi on 5 to the power of a third. But they shouldn't care too much about that. So yeah, there it is. Some simple steps to walk you through a related rates of change problem. Hope you've enjoyed yourself. I'll see you next time.